Here, I want to introduce the paper titled Depth with Nonlinearity Creates No Bad Local Minima in ResNets. So, we all know that deep learning has been an amazing success. It has been very exciting and great. In addition to many successful applications, there are a lot of good explanations as to why deep learning is doing so well. But one aspect of deep learning that is relatively not well understood yet is training. Training a deep model usually is done via high-dimensional non-convex optimization. In order to scale for high dimensionality, we usually have to use some local greedy algorithms such as gradient descent or its variants. But because of the non-convexity, local greedy algorithms can potentially get stuck near a locally optimal solution as illustrated in this figure. So, an important question is, for deep learning, what does the landscape look like? Does it look like something in this figure, or something more structured so that the use of gradient descent or SGD can be theoretically justified? In particular, residual neural networks or ResNets are shown to work well and are widely used in practice. Therefore, a more concrete question relevant to practice in deep learning is, do deep nonlinear ResNets have no bad local minima? One of the contributions of this paper is to prove that the answer is yes. More concretely, this paper proved the following statements for deep nonlinear residual neural networks, or ResNets. First, every local minimum value is exactly equal to the global minimum value of the learned representation. In other words, at every local minimum, a ResNet model is globally optimal with the learned representations. Every local minimum value is no worse than the global minimum value of the corresponding classical machine learning models and is guaranteed to further improve via the residual representation. Therefore, there is no arbitrarily poor local minimum for ResNets. These results theoretically justify why using ResNets is a good idea, and in particular, why it is better than classical convex machine learning models. The contribution of this paper can also be seen in the context of previous work. A previous paper shows that for ResNets with one-dimensional output, every local minimum value of ResNets is no worse than the global minimum value of linear models with fixed features. The previous paper in NeurIPS noted that generalizing this result to high-dimensional output is an important open problem. On the other hand, our paper shows that for deep ResNets with high-dimensional output, every local minimum value of ResNets is no worse than the global minimum value of linear models with the learned representations. This guarantee is better than the guarantee in the previous paper because we are taking infimum over W and R. To see this, one can set R to be 0, which recovers the previous guarantee. Therefore, we provide the strictly better and tightest guarantee in the sense that we obtained the equality guarantee, which directly recovers the upper bound guarantee in the previous paper. Moreover, we generalize the previous result to cover ResNets with high-dimensional output, solving the aforementioned open problem as well. Perhaps more importantly, unlike previous studies, our tight guarantee shows the important role played by residual block or residual representation, which is denoted by Z.